So we want to, we discussed that work has a definition. You can calculate work, and that is the scalar product of force and displacement. So it involves the force, involves the displacement. So in order to find work, you can see that it really depends on what kind of force that's doing the work. So so in this chapter, we're going to introduce several different forces. The first one we encounter is what we call the gravitational force. Now you have an object, okay, and let's say this object, I'm just going to let it fall. Okay, so if I let it fall, we know that this is a force direction. So Fg here is equal to mg, and it's going downward. That we all know because it's gravity. And if I let it go, if I just do it like that, what is the direction of displacement? Downward, right? So let's say this object is moving a distance d. So in that case, how much work is done by gravitational force? So we call that Fg, Wg. How much work is done by gravitational force? mgd, right? Okay. Why is it mgd? Because the angle, if you do this, this is your F times d, and then times cosine of the angle between it. What is the angle between it? Between the displacement and the gravitational force? That's 0. So when you plug into this equation, your F is mg, and you have your d, so you have mgd, and then cosine of 0, that gives you 1. So this is a force magnitude. And as you can see, your mass is a positive quantity. Your g is positive 9.8, and your d displacement is positive. This is the magnitude, so it's just a positive. So your work, if they are in the same direction, gravitational force does positive work. If it does positive work, what does that mean in terms of work kinetic energy theorem? Delta K is equal to what? From previous page, delta K is equal to work, right? This is how this is work kinetic energy theorem. The work is done to change kinetic energy. So, of course, there might be other forces present. So we should be like in general, we should say that it's net work. Okay, net work that's done by the force is used to change kinetic energy. So delta K is equal to the net work. And in this case, when the object is moving downward, the gravitational force does positive work. What does that mean? It means that this thing, let's say initial velocity is this, the final velocity is this. If the kinetic energy increases because this is greater than 0, it means that your final velocity has to be greater than the initial velocity, right? And if this and that is because from previous chapter 2, you know that the final velocity is greater than initial velocity. That is because it is accelerated by gravitational acceleration. But in this case, when you think about in terms of energy, we know that because gravitational force does positive work, and that work is transfer energy to the system so that the final velocity is greater than the initial velocity. So that's just the same thing, but from different perspective. This is from the energy's perspective, and in chapter 2, that's just based on the equations of motions. Okay. Now let's look at the other situation. You still have this object. Okay. You still experience the gravitational force, and that's still downward. But now, instead of letting it go downward, I'm going to toss it up. So if I toss it up, which means that it is moving in this direction, so that's your displacement. So in that case, what is the work done by gravitational force? Negative mgd, right? So the work done by gravitational force, again, we use F dot d. Your F here is your mg, and your d is still your d. And then cosine of, you can see that the angle between them, they are pointing in the opposite direction. So the angle between them is 180 degrees instead of 0 degrees. So now you have negative mg and d. So this is the case I'm telling you about earlier, that when you have a force, that force can do positive work or negative work. It really depends on its direction with respect to the directions of displacement. In this case, This is the direction of the force. This is the direction of displacement. They differ by 180 degrees. So gravitational force does negative work. What is the implications for when the force does negative work? It transfers energy from the system, right? So the system loses energy. So in other words, let's say initially you have this initial velocity, and when it goes up, it reaches a final velocity. And we found out because gravitational force does negative work, which means that the final velocity has to be less than initial velocity. And in fact, because it loses energy, because gravitational force is taking energy away from the object. And in fact, this is how you calculate the maximum height, because when you toss the object with the initial velocity, when it does not go all the way to outer space. Instead, it's actually reached the highest point, and it has to come back down. And that is because it's been losing energy. When it loses energy, the velocity decreases correspondingly. That's why you're starting with a non-zero value, and it's going to reach the highest point. When it reaches the highest point, the velocity becomes zero, and it has to go back down. Okay, so you can see that. This is the work done, gravitational force, that's negative mgd. This is also the work done by gravitational force, and that's mgd positive. It really depends on their direction. So whenever you do this kind of problem, you're given the force, you're given the displacement, you have to consider whether the force and the displacement, they are in the same direction. The force, they are not in the same direction of the displacement. They are not into the, you don't even have to consider because they do not contribute to work. And if they are completely in the opposite direction, then that force does negative work. Okay, so that's the important consequences of that. And so again, based on this work kinetic energy theorem, we know that when this is positive, then delta K increases. That we know. And then in this picture, because delta K is equal to net work, where in this case your net work is less than zero. When it's less than zero, you know that the final velocity has to be less than initial velocity because delta K is less than zero. Okay. So that is that. Any questions so far? Okay, so this is when you only consider gravitational force only. Let's say if we design a procedure in such a way that the initial velocity is zero, and we're going to bring, so let's say you have an object. And the initial velocity is zero. And during the move, you're going to move the object, like let's say upward. And once it reaches a certain distance, then it becomes stationary as well. So this is a situation that when you have initial velocity and final velocity that are both zero. So what do we get out of it? So let's say this is the object, okay? So you have gravity. The object experiences gravity that we know. And then you're going to apply a force to this object. So let's say this is the applied force. And initially, it is stationary. So initial velocity is zero. And then during the move, so you're going to move this object from this point to, let's say, another point. So once you move the object to this point, and then it becomes stationary again. So it loses all its kinetic energy. And at the same time, it still experiences gravitational force. And by Newton's first law, we know that there must be an applied force to balance that in order for a net force acting on the object to be zero. Okay? That all makes sense. Before the move, after the move, it has no kinetic energy because initially stationary, after the move, stationary. But during the move, we know that the object is moving with the velocity. But it doesn't really matter because that's an intermediate state. We're just looking at the initial state and the final state. So initial and final, it has no kinetic energy. Simultaneously, there are two forces acting on the object. So by work kinetic energy theorem, what can we deduce? So we have delta K is equal to net work, right? This is by work kinetic energy theorem. And based on this, scenario, What is the change in kinetic energy? Before and after the move, there's no velocity. So what is the change in kinetic energy? That will be 0, exactly. So you have 0 here. And that's equal to the net work. So what it means is that if initial and the final stage, they have no velocity, then there's no, the net work done on the, on the object has to be 0. Now the question is, what are the forces that do work on this object? We know there's a gravity, right? And so based on this picture, we have gravity. You also have the applied force. This force is going to do work. This force is also going to do work. So when you want to calculate net work, you really have to find out what are the forces. So you should have the force, the work done by gravitational force. So you should have the net work involves 2 terms based on this picture. One is work done by gravitational force, and the other one is the work done by the applied force. So I'm just going to use A, applied force. Okay? So what does that mean? It means that the work done by gravitational force has to be balanced by the work done by the applied force, so that the net work is equal to 0. Okay? So that's basically, so the work done by the applied force is simply equal to negative of the work done by gravitational force. Okay? All right, so any questions so far? That just basically introduced the concept that, when you have a system, when there are more than just one force acting on a system, in order to find the net work, you need to find the net force. You need to find, the work done by each individual force and sum them. And then in this case, that's equal to 0. That's because in this scenario, we do not allow the velocity to change. So initial and final velocity, they are 0. But there are situations that your delta K is not 0. In other words, the net work has a non-zero value, then that net work is going to use to change the velocity. Okay, so that's basically what it means. Okay, so those are, so the work done by gravitational force is easy because gravitational force is a constant. It is equal to mg. So long as you have your m, the mass is a constant, and your g is 9.8. So your force is a constant force. So this is the work done by a constant force. That's just the force times displacement. So that's easy, straightforward. Now, so the next thing we want to do is that, what about another force that is not a constant? It's actually, it's actually position dependent. So that is the spring force. Okay, so let's look at how the spring force, how much work is done by a force that is not a constant, and how do we go about calculating that? So let's say you have a tabletop, and then you have a block, and it's attached to a spring, and this is the wall. Okay. Now we all have the experience of playing with the springs, right? Yeah or no? Yes, right. So what does a spring do? I mean, so when you stretch the spring as opposed to you compress the spring, what do you feel? When you stretch, yeah, exactly, right? When you stretch it, so spring basically is elastic. So when you stretch it, you'll feel that it seems like it wants to come back to its natural state. And when you compress it, you feel that the force is trying to, oppose you so that it can reach its natural, unstretched state. So spring force. So there's a force acting on the object. Let's say if you compress the spring. So the spring is compressed. So you push it this way. So this is the applied force. Okay. So when you push this, let's say if you push this way. So this is your displacement. You push that so that the spring is being compressed. You feel that the spring wants to reach its natural, original state. So there's actually a force opposed that's trying to push it in this direction in order to reach that initial state. So that's the directions of the force. So this is the displacement of the spring, which is, because I compress it, so the displacement, the direction of displacement is in the rightward direction. And simultaneously, this spring wants to go back to this original state. So the direction of the force, we call that spring force, is in the opposite direction. So by Hooke's law, which I think everyone should know, right? So what does Hooke's law tell you? Or the spring, what is the restoring force? Hooke's law that describes the force and the position. That will be the spring force is equal to negative K and then times D. Now this K is not kinetic energy. This is a spring constant. For each spring, it depends on its elasticity, so it will have a different spring constant. So this is basically a constant, and your D is displacement. And as you can see, force itself is a constant, is a vector, and displacement is also a vector. So this is what we call the restoring force. Why do we call that a restoring force? Because when you compress it, it wants to be, it wants to reach its natural state. When you extend, when you stretch it, it's trying to, come back to its, again, its natural unstretched state. So this is what we call the restoring force. And by Hooke's law, the spring force is equal to negative times the spring constant and then times the displacement. Okay, so what does that mean when you have a force that is actually depends on displacement? Is it a constant? It's not a constant anymore. It's actually, it changes. It changes. The force matrix actually changes with the displacement. The larger the displacement, the larger the spring force. So now you have this. So how do we calculate work? If you remember, previously, we said that work is equal to F dot D. And this is when you have a constant force. Now your force itself is actually position dependent. You can no longer just use as simple as that. You can just no longer say, okay, it just replace your spring force with that, and then it becomes D, spring constant times D squared. No, it's not that simple. When you have a force that has a position as a variable, how would you calculate the work done by the force? By breaking it down so small that that within each segment the displacement is that force is a constant, and you add that those small sections of the forces, the sum of this. So in other words, how do we calculate work? You would say that. So instead of using this equation, you say if I sum up, if I divide the displacement so small and the force within that displacement is approximately a constant, then I can say that I have my the force. Let me see, how do I express that? So my force times that small displacement within that small section, and then I sum up all the small components. This is how you would do it. In fact, this is basically, so this is the force, this is the displacement, and then that's how do you calculate the amount of work? Then you just taking a small section, and your force now will reach roughly constant. So you can again apply this the definition F times F dot D. And they are in the same, in opposite direction. But regarding the magnitude, it's just the force times the displacement. So you have the force that can be treated as a constant, and times that small section infinitesimal amount of displacement, and that becomes the delta, right? Did I lose you? Okay. Yeah. Okay. Not yet, but it's just like the small interval, right? The delta, and then we're going to let delta to reach so small that becomes D. So does that ring the bell? Calculus, Newton's law, Newton's calculus. This is how you invent calculus. When you have something that varies, how do you sum up the sum? You just make it very small so that within this interval it becomes a constant, and then you just multiply this, and then you add that. So it's kind of like you divide small interval, and then for each one it has a corresponding force magnitude, and then you multiply them together, and then you add them all together, right? This is what we call calculus. So, yeah, so in other words, when you're dealing with a variable force, you have to use calculus to calculate the amount of work done by the variable force. And likewise, spring force is a variable force, so you have to use calculus. You cannot just directly use F dot D. That would not work, okay? And in fact, let me just mention that, when you have something like this, when you want to calculate the amount of work, when you have a plot that's force versus displacement, then the area under the curve will simply give you the amount of work, because just by this, this is this. The amount of work, that's basically the area under the curve, okay? And that's just basic concept from calculus. Now, how do we calculate the amount of work when you have a spring force that is not a constant? So again, based on this is summation of F and then times the delta x. So we're going to let delta so small that it becomes a infinitesimal, and then you're going to integrate. Basically, the area on the curve is integration. So you integrate this, so you have f and then times dx, and then your range is from from the initial position to the final position. Okay, so is it like too difficult for you guys? F dot D, and then integrate that? F dx? Okay, so anyway, this is what I'm going to do next is for your information, and then it will be good for you to come back to this like in a year or something. But this is just for your information during the derivation process. And then what you really need to know is the final result. Okay, so let me just briefly go over. How do we, when you have a force that changes, and it depends on the variable here, then you have to use calculus to sum up all the work, and then so you have your F times dx. So let's do that. So what is the work done by the spring force? The work done by the spring force then is your F and then dx, and then you have the initial position to the final position. Okay, so this is just by definition, and then we need to figure out what is the expression for the spring force. What is the expression for spring force? What is the expression for spring force? Negative k, and then instead of using d, now we'll just use the variable x, right? So you have so we're going to replace f with negative and then k and then x and then dx. So this is xi, xf. And in fact, if you're familiar with your calculus, you'll find that it's so easy to do. And what is this? So negative k, they are constant. Move the outside integral sign, so you have your x dx. So what is x dx? That's 1/2 x squared, right? Okay, so you have negative 1/2 k and then x squared. And then you have your xf and your xi, that's your range. Now we're going to plug into that, so the amount of work done by spring force is equal to negative 1/2 spring constant, the final position square, and then minus, and then you have another minus sign, minus 1/2 k xi squared. So what we have here is that you have, so negative, that becomes positive. So I'm just going to have this as a leading term. So you have 1/2 k xi squared and then minus 1/2 k xf squared. All right, so let's look at this equation. That looks very similar to 1/2 mv squared. That looks like kinetic energy, but this is actually the spring, the work done by spring force. Okay, so the work done by spring force is equal to 1/2 k xi squared minus 1/2 k xf squared. The initial position, final position. So by convention, usually we take the initial position to be 0. If we take initial position to be 0, then the work done by spring force is simply equal to, what is it equal to? Negative. What does that mean? It's negative. And then we're going to draw the F here. So it's just the displacement this x is in reference to the initial position. So if you take the initial position to be 0, then this is just basically any departure from the initial position. So this is the final result you need to know if you are not quite following the derivation. So the work done by spring force is equal to negative 1/2 kx squared. And x, regardless positive or negative, when you square it, it's always positive. So what does that mean? It means that the work done by spring force is always negative. It's always trying to take it's always taking energy away from the system. Okay, and that's why we call that a restoring force, because it always wants to get back to its original states. So this is an important result. The work done by the spring force, that's negative 1/2 kx squared. So we can use the same concept from previous, when we are dealing with the work done by gravitational force. Let's say instead of just one force, the gravitational force acting on the object, you have the applied force acting on the object, and then making the initial and the final state to be stationary. And we found that the work done by the applied force has to be equal to negative work done by gravitational force. Likewise, in this case, when you have a spring, you can apply a force to that, so you can stretch it or compress it. And so at any given time, there are two forces acting on the spring. One is the applied force, and one is the spring force. So that's it again. If we utilize this equation, net work done by the forces has to be equal to delta k. So in this case, if you now consider the applied force, the net work done consists of two terms. One is the work done by spring force, and the work done by the applied force. And if we say that if initial and the final velocity are 0, it just means that there's no change in kinetic energy. Then in that case, the work done by the applied force and the spring force has to be balanced each other. What I'm getting at is that the applied force is simply equal to negative of the work done by the spring force, and the spring force has negative 1/2 kx squared. And so what it means is that work done by the applied force or the external force is just simply equal to 1/2 kx squared. So they just differ by a negative sign. So it's the same analogy as same rationale as we did with the gravitational force. Okay. Any questions so far regarding? So you've learned that at least right now you learned that what the expression for work, what is F dot D. This will work only when you are dealing with a constant force. When you are dealing and then whatever force that you apply, if that's a constant, you can use this equation to calculate the amount of work. Now, if you're dealing with a spring force, we derive that the work done by spring force is not. You do not use this expression. Instead, you will use this expression. That's negative 1/2 kx squared. That will be the work done by the spring force. Okay, and utilizing the concept that the the work and energy theorem, net work done is to change the kinetic energy. Okay. All right. So, any questions so far? Now, the other thing I want to mention is that we mentioned about net work, which is the sum of the work done by the spring. Let's say, take for example, work done by the spring force, work done by the applied force. What you can also do to find net work is that if forces are constant, what you can do is that your delta K is equal to net work, right? And how do we calculate net work? Instead of saying that let's say you have three forces acting on the object. So work done by force 1, work done by force 2, work done by force 3. So you calculate individual work and sum them up to give you net work. Or you can actually just do this. You can just find out the net force. And then in the directions of the displacement. Okay, so this is basically you can also, so your net work, there are two ways of doing it. One is that you calculate individual work and then sum it up to find your net work. Or you do this, you simply find the net force and then do the scatter product of net force dot D. That will give you the same net work. Okay? So that's either one of them will be okay. Okay, so that is that. Let me see if I want to go over the rest of the stuff, the power. Okay. So we mentioned. Let me just briefly mention that. So this is the one that applies to the spring force. That's a one-dimensional. So you have F dot. You have the spring force times the dx. What about that instead of one-dimensional? If you have a situations that the applied force is not a constant, but it's actually in a three-dimensional case, how would you find the work done by this force that has x, y, z component, and they all changes in time, so that so you cannot just use F dot d to calculate the work done by that force. So how would you find that work? In order to do that, let's look at. We mentioned that by definition, work is equal to this. This is when you have a constant force. So if you have the force that is not constant, what you want to do is that you want to find the differential work. So how do you find differential work? Differential work basically is equal to F and then dot. Instead of a dot dx, now it's a three-dimensional, so we use a position vector. What is a position vector in differential form? Okay, so what is the symbol for position vector? Which symbol do we use that? R. Exactly, so we use R, right? But instead of using F dot R, now we have to use F dot dr because you have differential work, so you have this. This is for someone who knows differentiation. Again, that's for your information, all right? So you have F dot dr. So in other words, what you have to do is that if you have the x component of the force will have x, y, z component, and you have your dr has dx, dy, and dz. So when you do the scalar product, you will have the s component, and then dx, that's your x product. Now remember, this is a scalar product, so what you have is numbers. So when you do after you do the scalar product, you will have this term. You will also have the y component dy. You will also have the z component, and then dz. Okay, so you can see that the amount of work done by this variable force in three dimensions will have the x component dx plus the y component dy plus the z component of the force and dz. So what is the amount of work that's done by this force? You will have to integrate. So you have this, you have this, and then you have this. Okay. So this is just something that you break it down into the x and y. X component, y component, and z component, because the displacement in the x and y, z may not be the same. So you have to actually have the horizontal force component times the horizontal displacement, and then integrate that, and then you have the vertical component of the force times the vertical displacement, and integrate that, and so forth. Okay, so that's basically that. Okay. So let me see what else. Now, the last concept from this chapter that I want to go over is what we call power. Okay. So what is a power? What is power? Just by the common usage, when you hear people that power, what do they exactly mean? What is power? Or we hear the common usage that power outage. What exactly does that mean? Yes? Energy? Uh-huh. Yes? Watts. Okay, so the unit for power is watts. Okay, so have you looked at the electrical bill and how much you're paying each month that you're being charged? No? Okay. Next time you can just take a look and see how the electrical company they charge you and stuff, and then you can find some familiar units. Okay, so what is power? Power basically is defined as the time rate of energy that's being done, time rate at which work is done by force. So that's the definition of power. So it involves the work, involves the time rate. So what does that mean? Time rate at which work is done by force. So the symbol for power is P, okay? And it involves time rate of work. Time rate of work, which means that the amount of work that's done by force per seconds, right? So time rate. So involves the work, involves the time interval. So this is the definition of power. The amount of work done by the force over the time interval, and that's your power. So we can see that you have this, and then the unit is watts. In honors who? Watts, right? Yeah, I think in honors of watts. Okay, so this is the power. So, and this is what we call the average power. It's not instantaneous power because you're calculating power over a time interval, and that time interval might be a longer interval or a short interval. But when you have, let's say, you find the amount of work that's done by this force over this time interval, and you take the ratio, that gives you the average power. But sometimes we're not interested in average power. We're more interested in instantaneous power. So we drop the average. How do we find the instantaneous power? Again. Yes? Exactly. You take the differential form. So if you shrink the time interval so small that they become a constant, then within that small segment, your work becomes differential work. Your time becomes differential time. So you have dw dt. That's your instantaneous power. Okay? And so if you remember, we mentioned that your work done by the force is equal to F dot D, and your dW, differential work, is equal to F if we're just doing the one-dimensional. So you have FD and then FDX. So now I'm going to replace the D with the X, with the variable X. So now your D here becomes, let me just do this to be consistent. So force, the scalar product of force and the displacement. So this is when you are dealing with the constant force. If you are dealing with, let's say a variable force, then the differential work is equal to the force and then times, instead of x, now it's times dr, right? Okay, so you have your dx, so f dx, and I'm missing any term. So in vector in this you have, so dw should have this dot dx. So in this you have the force magnitude times the displacement, that's dx, and then what? Am I missing anything? F dot dx, that will be f times dx and then times cosine, exactly, cosine theta, right? So there's always the cosine, whenever you do a scalar product, there's a cosine of the angle between them. So you have f times dx and times cosine theta. So you have your dw that is in this form, let's say in a one-dimensional case. So how do we express that in terms of, plug into this equation to find out, what the power, expression for power should be. So your dw, we already know that is force times the differential dx and then times cosine theta. So in the numerator you have f times dx and then times cosine theta, and then over you have the dt in the denominator. So what we have here is that you have the force that's not changing. What is dx over dt? Dx over dt, time rate of change of position, that gives you velocity. So you have fv and then times cosine theta. So your power can be calculated if you know the force magnitude, if you know the rate or the velocity, and then times cosine theta. Again, you can see that force is the vector, velocity is the vector, and they multiply, you use their magnitude f times v, and then times cosine theta. So you have two vectors and then times cosine theta. That will give you in vector form, what kind of product would that be? Huh? scalar product. So you have vector force, scalar product, velocity, right? Because F dot V, that just gives you FV cosine theta. Okay? So this is another expression for power. The definition average, of course, is this. Very simple. If you know the time, during that time interval, if you know how much, the amount of work that's done by the force, you can just use that to calculate average power. If you're asked to find the instantaneous power, you can use either this, which is FV cosine theta, or just F dot V. Okay? So that's basically, and you can see that this is actually very similar to work, because what is your work? Your work is F dot X. So when you do the time rate of change of time rate of change of work, that just basically, the position, the displacement now becomes velocity. Okay? And the other thing I want to mention is that in United States, we use watts for power. And there are several, different units that's also very, let's say, so 1 watts, that are also very used commonly. So 1 watt, you can just drop the ATT, so just 1 W, that gives you the wattage. And so watts, just by definition, work has a unit of joules, and time has a unit of seconds. So that's also equal to joules per second. So joules per second gives you 1 watt, and now this is in United States, and also most part of the world we use watts for power. Okay, but there are some instances that say the car, or in England they use horsepower. So 1 HP. How is it 1 HP? The horsepower in relation to watts, it is actually equal to, after you do conversion from the SI unit to the British units, you have 746 watts. So this is how they relate to each other. 1 horsepower is this amount of wattage. And if you look at your electrical bill, they don't use watts. They actually use, they calculate how much energy that you use comes through in your home, and then they calculate your electrical electricity usage. So they use kilowatt hours. Okay, so we can actually quickly calculate how much kilo hours. What does that give us? 1 kilowatts, and then times hour. So kilo is 1,000, right? So you have 1,000. We change the kilowatts to watts. So you have 1,000 watts, and then times the hour. We change that to seconds. So watts times seconds. So what is hour? 1 hour is equal to 3,600 seconds. So what we have here is that you have a huge number, which is 3.6 times 10 to the 6. And then watts times seconds, what does that give you? Watts times second, that gives you joules, which is the units of energy. So 1 kilowatts hour, that gives you 3.6 times 10 to the 6 joules, which is 3.6 megajoules. Okay. So next time when you look at your electrical bill, see how many kilo hours that's been used in your home, and then convert it to how many joules that used in your household, and that just gives you some idea. Okay. All right. So I'm going to stop this.